In this video, I'm going to be going over electromagnetism and how it relates to the direct current motor, which uses a direct current to produce mechanical force. And thanks for watching. And Otto thanks you as well. So to begin, ancient Egyptians recognized electricity observing the electric catfish. While these treatments had no actual medical efficacy, they do represent humanity's earliest recognition of electrical phenomena and attempts to harness it. This is what the electric catfish looks like. Here's a diagram of its electric organ. And this is the ancient Egyptian relief depicting electric catfish. It was recognized that these fish could deliver painful shocks. The Leyden jar was the earliest attempt to store an electric charge, and it represents the first capacitor, which is a device that stores electrical energy. As a fundamental understanding, electric charge is a basic property of matter discovered through observation of amber attracting small objects when rubbed. The term electricity originates from the Greek word electron, meaning amber. This simulation is a great visual representation of static electricity using a balloon. And when you rub the balloon on the sweater, you collect all of the negative charges. And because like charges repel each other, when you bring it close to the wall, it pushes away the negative charges. And because those negative charges are being pushed away, when you let go of the balloon, it gets stuck there. But if you pull it away and you let go of the balloon, then it gets stuck to the sweater because the negative charges are attracted to these positive charges. And the balloon is only attracted to the wall when it's very close because the negative charges have been repelled. See, at this point, not enough negative charges have been repelled and it's more attracted to the sweater. But when it's very close, the negative charges are repelled enough such that the positive charges are exposed and it gets stuck to the wall. Coulomb's law quantifies the force between charges. Opposite charges attract, the same charges repel each other, and neutral charges have no effect. And the distances play a role in the strength of the force. The closer you are, the greater the force. And this is actually similar to gravity. If you look at Coulomb's law and the statement made by Isaac Newton, the forces of planets, they look kind of similar. William Gilbert invented the versorium in 1600 to detect electric charge. The versorium is simply a needle constructed out of metal, which is allowed to pivot freely on a pedestal. It's of a similar construction to the magnetic compass, but is influenced by electrostatic rather than magnetic forces. 154 years later, John Canton invented the pith ball electroscope, and then the gold leaf electroscope was developed in 1787 by Abraham Bennett. These were early ways to detect charge. Now that we understand what charge is, electromagnetic fields are created by moving charges, and they exert forces on other charged particles. The presence of either a positive or negative electric charge produces an electric field. The motion of electric charges is an electric current and produces a magnetic field. This is a basic visual representation of the magnetic field and the electric field. This is what an electromagnetic wave looks like. The Lorentz force describes how charged particles interact with electromagnetic fields. And Faraday's law of induction describes how changing magnetic field induces an electromotive force. The word flux comes from Latin meaning flow or stream, which describes how fields move through space. This equation describes the force applied to a charged particle, where Q is the charge, E is the electric field, V is the velocity, meaning the direction, and B is the magnetic field. So it factors in the electric field, the magnetic field, and the velocity, and the charge of the particles. And this is what determines the acceleration of a particle within an electromagnetic field, because a force relates to acceleration, meaning you're applying something to a particle which moves it in a different direction. And Faraday's law of induction describes how changing a magnetic field induces an electromotive force, meaning a current. But this is a very basic recognition. I will demonstrate an electromagnet using this simulation. This is from the University of Colorado, Boulder. This is a basic explanation of an electromagnet. When there's no current, there's no field. The movement of electrons is what produces a magnetic field, similar to how a bar magnet produces a magnetic field. The movement of charge creates a magnetic field, and that's described here. The motion of electric charges is an electric current and produces a magnetic field, which is what we're seeing right here. When there's no motion, there's no magnetic field. When there's motion, there is a magnetic field. A bar magnet produces a magnetic field. If you move the bar magnet, it will create a current in the wire. And this is the fundamental of every single electric motor. A changing magnetic field causes a current in the wire. And that's what Faraday's law describes. Faraday's law of induction describes how a changing magnetic field induces an electromotive force. To be very clear, that's exactly what's happening here. The magnetic field is changing, and thus it's producing an electromotive force. So that's a general introduction. And Maxwell's equations were what brought it all together. Electric currents and changing electric fields generate magnetic fields, and the changing of magnetic fields produces electric currents. And Maxwell's equations first appeared in fully developed form in 1873. So now that we have a basic understanding of charge and electromagnetic fields, we'll briefly go over electrochemical reactions. Batteries convert chemical energy into electrical energy through reduction oxidation, redox reactions. I'm not going to get into the specifics of the chemistry, but this is fundamentally how chemical energy is turned into electrical energy. In 1780, Luigi Galvani discovered animal electricity. He was doing experiments on frogs' legs and noticed that the frogs' legs twitched. They used frogs for various experiments at the time. And Volta was the one that showed that the frog's legs muscle twitching was due to static electricity. And Alessandro Volta in 1800 developed the voltaic pile, which is the first true battery capable of producing steady current. This is a diagram showing the voltaic pile, similar to the galvanic cell displayed earlier. You can see that zinc and copper were used in the voltaic pile, the redox reaction. And this is what a voltaic pile actually looks like. And since then, over time, batteries have been achieving much higher energy densities. We still have not seen a limit to the energy density of a battery. Lead acid batteries are still very common in vehicles. In 1859, Gaston Plante first invented the lead acid battery, but lithium-ion batteries are becoming more common. Jacobi in 1834 created the first practical rotating electric motor capable of significant mechanical output, producing approximately 15 watts of power, and was able to power a boat carrying 14 passengers, reaching speeds of about 2.5 kilometers an hour using zinc batteries, which showcased the feasibility of electric propulsion. And Jacobi published detailed documentation of his motor in 1835. Widespread adoption was limited due to the high costs and inefficiencies of battery-powered operation. But it was a significant event. This is what a replica of the motor that Jacobi created looks like. And you can see in the bottom right, this is the battery. These are the specifications of the motor. Brushed DC motors convert electrical energy into mechanical energy. And if they're powered by a battery, you could argue that they're converting chemical energy into mechanical energy. They're known for high torque at low speeds, and the efficiency ranges are very high, 70 to 90%, but decreases with load due to frictional losses in brushes and commutators. And this is what a DC motor looks like in operation. You can see the positive and negative at the bottom, which is the current going through it. And as it rotates, it changes the direction of the current in the wires. And to be clear about the brushed DC electric motor, since the brushes wear down, the brushes are the contact of the charge to the commutator, we have brushless DC motors. Instead of these connectors here, it instead uses an electronic controller, where a sensor detects the angle of the rotor and it has a switch in it rather than relying on the rotation itself. The elimination of the sliding contact allows brushless motors to have less friction and longer life. These are my sources for the video. If you have any questions, please let me know. I learned a lot during the process of creating this video. I hope that you were able to learn something as well, and I appreciate anyone who's been watching. There are still many things yet to be covered.